You're good to go.
Okay, so welcome. This is, or at least I hope this is to talk about Syscall's ARMS. Basically, this is my attempt to do an introductory level brief on how exactly ARMS assembly works. One of the things that I ran into is years ago I got asked to do an x86 assembly course. Then they asked to do an ARM assembly course. This is sort of what happened while I was trying to figure out how to get ARM. Okay. For what it's worth, my name is Frank Waters. I work for Telecommunications Incorporated. You probably know us as AOE, Art Exploitation. We have a booth. We've been showing out some Raspberry Pis. In fact, the reason we have those Raspberry Pis is that's the data we use for this particular class. It's the class that a lot of this is based on. I'm a developer instructor there. Primarily I do Windows, but again, I do whatever I get asked to do. In this particular case, I got asked to do ARM. It's a heck of a lot of fun. So, none of you probably care. I have an MS in computer science, systems programming and security, and I also have a degree in the history of science, 17th century astronomy with a specialty in Latin. So clearly I can decide what I want to do with my life. So, this is going to be a pretty intense talk, I have to admit. So one of the things I'm trying to do is lay this out in some way that people can understand and find some way to bring something out of this. And so basically this talk can be split up into a couple sections. First is, what is an ARM chip? Why do I care about it? Is there something that I can cling to for dear life? What exactly does an ARM assembly file look like? How addressing works? And finally, hello world. Okay? We're going to try over the next 40 minutes or so to bring people from maybe knowing nothing to being able to print hello world to screen on an ARM chip. Okay? So, a graphical representation of what we're attempting today. Basically, I know I want to learn how to code. I'm going to choose assembly, and I'm going to do it in 50 minutes. Okay? So, first part, what the heck is ARM? A lot of you guys probably know what ARM is. Frankly, it's just a microchip. That's all it does. Probably my advanced architecture professor somewhere in Tallahassee right now is really excited that I'm standing in front of a group of people saying, fetch, decode, execute, store. Okay? That's all chips do. That's all any chip does. That's what it does. ARM does it a little bit differently than the chips we're used to, but frankly, in this particular case, we're just talking about a chip. It's a RISC architecture, which we'll go into in a second. And it's become incredibly popular for mobile devices, tablets, phones, everything out there, cars. Now, one of the things that I find interesting is, despite the fact that this has become such a popular platform, it came about in the 80s. How many cell phones were there in the 80s? Not so many. Okay. So, how did we get here? A long time ago, in a galaxy far, far away, we had Syscall architecture, which is complex instruction set. That's all Sys stands for. And what this was complex instruction set computer chips. Did their best to mirror some high-level language. When I say high-level language, I'm talking about C, something up there that's high. The reason it did this is it tried to take a single line of C and implement that single line in the chip. But it couldn't do that in one line. So often what happened is that one line of code got pushed to the chip. The chip then had to go to the repository of instructions that were on the chip itself and run a bunch of instructions. And only when it was done running those instructions did it turn around and figure out what was going on. What this caused was, frankly, larger chips that required more power, chips that had to support whatever got pushed out from the compiler. And one of the things is it made for a larger chip, slower response times, and it took more memory, and in the 80s, memory was at a premium. So, why on earth did we go about changing architectures? Since I just said that it was larger, slower, used more power, there's a bunch of reasons to do it. Sometime about the early 80s, I think it was actually 1980, David Patterson, one of the saints in the computer science field, came forward with one of his graduate students who wrote a paper called The Case for Reduced Instruction Set Computer. Frankly, because I like chips, I think this is a watershed moment in computer science. Because basically they say, hey, let's abandon everything we've been doing in this complex instruction set. And let's try and cut this down to the bare bones that we need. He said, we'll make it a smaller chip, we'll put the problem on a compiler, because the compiler is now going to have to spit out more instructions because I don't have that ROM chip on board anymore. And basically what resulted is, if you can get away with taking out the slowest instruction on a chip, what happens to the clock cycle? It's faster. Your clock cycle is determined by the slowest instruction. Take out the slowest instruction, your clock cycle goes faster. Okay? So they went through and they pulled out slow instructions. One of the fun things about ARM, there is no div instruction on ARM. Simply because the div instruction takes a lot of time, and by getting rid of it, they have to increase the clock cycle. So, one of the things that I ran into is, I really wanted to know what on earth made a RISC chip a RISC chip. One of the best definitions I think I've seen so far is the simple load store architecture. If you can only do, if all you can do with memory is go get it and put it in the chip, or take it from the chip and put it in memory, it's a RISC processor. Really straightforward definition. Anybody's played around with x86, you know that you can do things in memory without putting it into the register first. You can't do that in RISC chips. The other thing is, when we take a look at the transistor count of associated chips, you can see that the ARM chips down there at the bottom have much fewer transistors. Again, if you're powering the chip, the more transistors you have, the more power it needs. What it's worth, the brand new Samsung chip on the iPhone 5S, that is $1 billion. So one of the things you see an increase in ARM. ARM is trying more and more to steal as much market share as it can from the x86 world. And meanwhile, you see the x86 releasing stuff like Haswell processors, which are using less power. So you've got ARM processors trying to push more, and you've got Intel trying to pull down their level of power. Okay. So, you're wondering, we've talked about what ARM is and what RISC is. Now let's talk really quickly about what happened here. Right. So, the happy speech is, we had about 5 ARM chips on Earth for every man, woman, and child that walks the planet. That's kind of a lot, right? How many smartphones are in this room? Probably 7. Probably a lot of this conference. Okay? And they're reporting that they're shipping something like 16 million ARM processors every day. So this is going up pretty quickly. So the fun thing is you hear stories every now and then about people who have these ARM chips. You know, this is running Linux. If you can code C for Linux, you can code something for this device. It's really wonderful until you think about the fact that people could keep putting these devices in everything. From cars, thermostats, cell phones, everything. One of the most interesting stories I've seen was in 2011, the Chamber of Commerce in DC got hacked. They hired a company to come in and go through their entire network to see what was going on. They discovered that their thermostat was beaconing out to China. I mean, I love this story. Who on earth is going to go ahead and check to see if your thermostat is up to date? How many people would expect an implant to be on a thermostat? But the things run in Linux. Simple socket-based programming can be computer. And I doubt many people run antivirus on their thermostats. Okay. So what wound up happening is, completely by accident, if you will, RISC processors got pulled in by the mobile world and never foresaw. RISC itself was just trying to be faster, smaller, better. And when the mobile industry came around and looked for a chip, why not? There's a chip out there, it's small, it's fast, and it does everything we need it to. And so one of the things that's happening, like I mentioned earlier, is you've got this sprint from ARM to expand what they can do, and Intel and x86 to try and shrink the amount of power that they need to do the same job. And it's kind of interesting because the watershed that here that's going to happen is moving to 64-bit. There are a lot of people that have been pushing ARM as a server platform for the simple reason that cooling an ARM chip is way cheaper than cooling an x86 chip. And the other thing is it takes up a tiny amount of space. The Calzada 2U server that they have has 192 cores in a 2U rack space, which is kind of awesome. The only thing that's been keeping it from happening, keeping it from going further, is the fact that up to this point, ARM has been a 32-bit architecture. Everybody keeps talking about releasing 64-bit, and because 32-bit can't address the kind of memory that some servers need, it just hasn't been really copied. However, guess what just got released in the iPhone 5? The first 64-bit ARM chip. AMD has declared that they'll have that ready to ship next year. It's kind of fun to see exactly where that's going to go. Okay, so now that we're about to get started in the actual programming portion, I find it useful for myself to grab onto some concept, some central theme of what I'm working with to try and make sense of all of the incoherence that starts. Right? Everything has a challenge that has to be worked with. If you're talking about a mobile platform, the one thing you don't have to worry about is power. If you're talking about programming, you're going to have to worry about security. In this particular case, what is it about the ARM chip that determines every decision that's made about that chip? Okay? We're going to talk about the registers. We're going to talk about the instruction layout, the fact that the instruction layout itself has its own limitations. We're going to talk about the fact that this is a RISC chip. I just defined that as a load and store, right? And we'll also talk very briefly about pipelining, which is kind of fun. Okay. So, how many people in here have programmed with an x86 assembly before? Sweet. This is going to be very easy. How many people went to Road Clown's talk? Okay. I was very happy. It made a lot of sense. I enjoyed it. But one of the things that you'll find is if you program x86, you know the fact that it's a pain in the butt because really you only have 4 registers that you can play with. They're called 4 general purpose registers, but really each of them has their own purpose. So you can step on yourself really quickly. One of the things is that ARM tends to limit the amount you do with memory. And in order to make that a little bit better, they've increased the number of registers that you have at your disposal. Instead of having 4 general purpose registers, you've now got 6 or 7 general purpose registers. Sorry, you've almost got 10 general purpose registers, my apologies. Okay. Now, the other thing is we have to bear in mind that every instruction that goes into an ARM chip fits on a 32-bit bus. Okay? Every instruction is 32 bits. Yes, if you want to stand up and complain about the thumb instructions, we can do that. Please don't, because this is going to be fun enough. Almost nobody uses thumb instructions, so I'm going to stick with the normal 32-bit instructions. Okay? Now, the other thing is that ARM abides by the simple definition of RISC. We can't play with anything when it's in memory. We have to take it out of memory before we do anything. Okay? Now, finally, pipeline. The only reason I'm hitting pipeline right now is because when I cover addressing, if I haven't covered pipelining, that's going to be a little weird because nothing's going to look right. Nothing's going to line up correctly when I talk about this. When I talk about addressing, I haven't talked at least briefly about pipelining. So, let's start with that. Pipelining is actually a really simple concept when you think about it. One of the best examples I can ever think of is imagine if you're in a classroom. You've got a bunch of students, you've got a roll of sheets of paper in front of the classroom, they've got just straight up math problems. Okay. The student comes up, pulls the problem out of the bowl, calculates the answer, pulls it out of the bowl, reads it, calculates the answer, writes the answer back on the sheet of paper. Okay. Simple 4 steps, right? Pull it out, read it, calculate the answer, write it back. Right. 4-step process. So imagine if each of these steps took exactly 1 minute. 1 minute to take something out. 1 minute to take a problem out of the bowl, 1 minute to read the problem, 1 minute to do the problem, 1 minute to write the problem back. Right? If that's the case, how long does it take to do one problem? 4 minutes, right? 4 steps, each 1 minute, 4 minutes. If I wanted to do 4 problems, 16 minutes, right? 4 problems, 4 minutes per problem, 16 minutes. So one of the things is pipelining gets around this by finding a better way. Simply because somebody's standing in front of the room reading the problem doesn't prevent another student from going up and grabbing the problem out of the pool. This is all pipelining is. It's making sure every single thing that can be used is used. And here's an example of what happens when we stack the actions. In minute 1, the first student comes up, pulls the problem out of the bowl, pulls the problem out of the bowl. Minute 2, student 1 is reading the problem, student 2 has come up and pulled the problem out of the bowl. Minute 3, student 1 has calculated the answer, student 2 is reading the problem, student 3 has come up and grabbed something out of the bowl. Does this make sense to everybody? And we can see that if we keep this going, we can actually finish 4 problems in 7 minutes. Which is way better throughput. Frankly, ARM is just the same way, at least with the early one. You can see basically that this is split up into 4 sections. You've got getting the problem, reading the problem, basically calculating the answer, then writing back the answer. This is an early 4-5-stage pipeline. In the ARM processors, I think they're up to 9 for some modern ones. This is nothing compared to the charming 32-stage or 26-stage pipeline that you'll find in the PM4s. It's just absolutely absurd. Okay, so let's talk really briefly about if we pop open an ARM assembly file, what it's going to look like. Okay. There are a couple of assemblers out there that we can use. Frankly, I'm cheap. I imagine most people use really want to. You'll find me using the G&E ARM assembler. It's free. Yeah, it's called gas. We refer to it all the time. You can go out and buy some. I've never bought one because gas is fine for me. You can if you want to. Okay. When you look inside an ARM file or an ARM source file, you're going to have lines that consist of either assembler directives, instructions, labels, and if you're not a real coder, you might have some comments in there somewhere. Okay. But that's all you're going to see. For assembler directives, there are a bunch of them, but we really don't care about too many of them. The ones that I'm talking about here, the dot line. So anybody familiar with x86, this is going to be a little bit weird. But because we're using 32-bit instructions, they have to be byte aligned in 4 byte chunks. It expects to see that. And if for some reason you have some variable or some string that's ahead of it, you have to go ahead and realign it, and that's all dot align does. It says, hey, let's recruit here, and we're going to start from here. Now, dot data should be familiar to anybody that's on x86. That's just saying, hey, they're variables here. ASCII just says, hey, the data that's going to follow this is an ASCII string and terminate with a 0 character. Global just says, make whatever is in front, whatever comes after this is a global variable, everybody can see it. And we'll get back to those in a minute. So, when we talk about labels, labels are just like x86. It's some one word followed by a colon. Okay? All this is a placeholder for you to be able to figure out what's going on. When it gets assembled, it's going to be taken out, and all references to it will be changed to a hard-coded address value. Just a 32-bit hard-coded address value. Now, moving on to the fun part. How exactly do we go about Syscall? That's the whole point of this talk, so let's go with it. So, most of you guys probably are well aware of the fact that you've got this user mode kernel and dynamic. The user mode process doesn't get to do whatever it wants to. In fact, it doesn't get to do a whole heck of a lot. It has to ask the kernel for everything. If, say, a user mode process wants to write a file, it has to say, hey, kernel, I'd really like to write this file. And the kernel will give it a handle to that file or some way to access that file. But still, that user process is going through the kernel to get whatever it needs. A user process has to talk to the kernel to do anything it wants to do. And in this particular case, when we talk about syscalls, syscalls are how ARM goes about talking to the kernel and getting the kernel to do what it wants to do. Okay? So, one of the most interesting things I've run across is the effort to find some amount of documentation to talk to ARM assembly. There's really not a whole lot of books out there. The best one I found was by a guy named Steve Ferber called System on a Chip. One of the reasons I like it is because it's got a lot of wonderful data flow diagrams, if you like that kind of stuff like me. But all of the examples he gives crash miserably when you try and run them. And probably that's because it was written almost 15 years ago. For some reason, in the last 15 years, they've changed the way they've done this, and this is the heads up if anybody wants to go on and try this. You may see reference to something called a software interrupt instruction. It's an SWI instruction. This doesn't work anymore at all. And this resulted in about 2 days of me reading my candidates the wall until I found Shellstorm, which is an absolutely wonderful website if nobody's been there. It has shell code for ARM chips, and one of the great things is because I was able to find that shell code, I was able to basically reverse engineer how exactly he managed to do what he wanted to do. And so from that, I figured out that the SWI call has been replaced with a service call, or SBC. Okay. So if you see SWI with hex code 12345, that doesn't work anymore. So you're going to have to replace it with the service code. Okay. Now, how exactly do you make a service request? Back in the old days of Windows simply, you had to put code in AH. In Linux, same thing, you have to put a code to say what exactly you want in the syscall. It's no different when we talk about ARM. The only catch is, for some reason, I'm sure there's a good reason, but I haven't bothered to look it up. Register number 7 is the register that holds whatever code you want to have a syscall. So that particular number is actually just an offset into the syscall table. So whenever you ask the kernel to do something, you populate that R7 with an offset in the syscall table. The kernel then goes to the syscall table, takes that offset, goes to that location in the syscall table. The syscall table is just a table full of 32-bit addresses. Those addresses correspond to the code that does whatever thing you want it to do. So if you wanted to go ahead and call something with the 5th offset in the syscall table, the kernel goes to the syscall table, finds the 5th entry in the syscall table, executes whatever code is sitting there. So you can think of it like Windows SSDT, System Service Dispatch Table, if you like Windows that way. So the way that we get parameters in is just like DerbyCon talked about yesterday, and that's by putting them into registers. First parameter goes into R0, second parameter goes into register 1, third parameter goes into register 2, and register in goes into parameter in goes into register in -1, all the way up to 7. Make sense to everybody? Because if you're going to call a syscall table, if you're going to call a syscall, you're going to have to do the data work. Okay. One of the fun things is this is no direct stack access for those of you who play around with Windows assembly. This has been a refreshing change, right? You don't have to worry about the prologuing anymore nearly as much. So let's actually do one of these. Let's talk our way through a really simple syscall. Okay. So in this particular case, we're going to use exit. And for what it's worth, the exit is the second entry in the syscall table, so we're going to have an offset of 1. We're all good computer scientists, we start counting at 0, right? Okay. So the second entry is going to be an offset of 1. Exit only takes one parameter, and that's the exit status. So why did I leave it? Okay. So exit doesn't return any value, so we don't have to worry about that. Because why would you return a value if you're not actually going to go back? Okay. So let's talk about this. First thing we need to do is, I can't see it from here, but underneath start, you see move R7, pound 1. Count is just a way for ARM to say this is a literal value. This is just 1. Move 1 into R7. Okay. Move 0 into R0 and call service 0. Okay. That's how you make a service call. This is the simplest service call you can do. Populate R7. The only thing we're passing into R0 is the exit code we want to go. And then we call service 0, which is the way to say, hey kernel, I want you to do something. And the kernel goes, great, grand, wonderful, looks to your registers to see what's there, does whatever you asked it to do. Straightforward for me, sense, right? Okay. So let's talk really briefly about addresses and addressing. I know this is a topic that everyone loves. Everyone loves pointers. At no point in any class that I've ever taught has anyone ever tripped over pointers. Okay. So now we'll talk about actually getting it to do something. Okay. I want us to actually print out hello world. To do that, we're going to have to talk about addresses. Okay. The one thing to remember when we're talking about dealing with addresses in ARM is how long are all ARM assembly instructions? 32 bits. How long are addresses? 32 bits. How in the name of all things holy am I going to get an instruction and an address into a 32-bit space? Okay. This is where ARM has a little bit of trickery. Okay. So, clearly this is not going to work. If you're a complete masochist, what you can do is you can actually base it off the PC register. So the PC register inside ARM is just like the EIP register in x86. All it does is the program counter points, PC's program counter, apologies. The program counter just points to the next instruction. In fact, whenever I teach assembly, I usually shout out at regular intervals, where does PC point to? And hopefully by the end of several days, the students all say, it points to the next instruction. This is a fundamental truth. It will always point to the next instruction that's going to be executed. It will always point to the next instruction that will be executed. That's all it points to. That's all it will ever point to. And if it points to something else, that's going to be the instruction that's about to be executed. Okay? That's it. That is all the PC does. Okay? So, one of the things that we can do is because in most cases, if we're talking about moving or jumping or going ahead and changing the way that we do something, we're going to be referencing memory that's close to where we are. And so one of the tricks that ARM does is it just goes ahead and says, well, if I want this address, I'm going to modify whatever value is in PC and dump that value into a register. Okay? Well, I'm about to execute this line. I want to reference something that's 12 lines above me. Okay, 12 times 4 bytes, because each instruction is 4 bytes, 48. Okay? So you'll see it say PC minus 48. Okay? Straightforward. This way we avoid the problem of having to figure out how we get a 32-bit instruction in addition to an operation into a 32-bit instruction. Sorry, 32-bit address into a 32-bit instruction. Yeah. Alternatively, if you didn't like having to do all this calculation on your own because it's actually kind of miserable, and we'll talk about why in a second, there are two instructions. The ADR instruction is a pseudo instruction. The LDR instruction is an actual instruction. And we'll talk about what pseudo instruction means right now. In the next slide. So here's an example of what we're talking about when we're talking about going ahead and modifying PC. In this case, the assembly code complete. All I'm doing is I'm saying, hey, I'm calling the printf function, and if I'm calling the printf function, I have to give it an address for a string. So I'm moving the address of my string listed here into R0. I'm simply doing that by subtracting the program 28 from the program count. And this is where things get a little bit strange, because if you talk about 28 from the program count, how many instructions is that? 28 bytes, 4 bytes per instruction, 7 instructions. Does that make sense to everybody? We can also pull out the fact that we have 16 bytes for that, the string itself. And so we're down to 12. If my math is all good. Hopefully it is. So then we have 3 instructions. How many instructions are above sub? program counter is pointing to the instruction after sub, we're still missing. This is where pipelining comes in. Okay? If you want to talk about exactly how we go about doing this, understand that by the time that we've actually evaluated this instruction, the program counter has changed to point to another instruction. That's all I want to give people to understand when we talk about the program counter and about pipeline. Okay? And you can see in the object on the other side here that we keep that sub and it moves up. Okay? This is foolish, no one should ever do this. Please don't. I just wanted to see people, I wanted people to see that that's how it happened. Because the next thing we're going to talk about is we're going to talk about the ADR pseudo instruction. It's called a pseudo instruction because at the time it actually gets assembled into a sub instruction. Or an add, depending on what you want to do. Here you can see it's the exact same source, except instead of the sub, I use ADR. And I just said move the address of my string into R0. If you look over at the object dump of what's going on, that's assembled into a sub instruction. It's all done for you. Okay. Now the big problem is right now, I'm changing memory. It's instructional memory. I have no .data section in this code. Linux doesn't really like you changing this stuff. So if we wanted to, we'd have to go ahead and add a .data section. Because the .data section is stored somewhere else, we can't do this trick of using an offset from the PC. Instead, you're going to want to use the LDR instruction. So if you really wanted to dig into why you have to do that, the fact is that when we talk about an assembly instruction, because it has 32 bits, we only get 12 bits when we want to move intermediate value. So if you want to move an address in, you get to move 12 bits in it. That's not going to work. Right? That's why you use the sub. That's why you use add. Okay, so basically, if it's out of a range of about 1,000 instructions, you can't get to it. So to do that, we actually go ahead and use something called the LDR instruction, which flat out just pulls data out of memory and moves it into a register. All LDR does. But what this winds up having to do is we have to store a 32-bit value somewhere so that we can then load it from memory. This is where what's called literal pool comes in. It's a lot of fancy words, but basically, all that's happening is when we use the LDR instruction, it's the LDR R0 comma equals my string. You're saying move the value from my string into R0. It's slightly complicated because what winds up happening is it takes that 32-bit value that corresponds to the location of my string, and it puts it down at the end of the program. You can in fact see it located on the object docket 83AC. So what this is basically saying is you get the offset from the program counter that points down to the location that contains the 32-bit value that you want to move. Okay. Does this make sense to everybody? Maybe. Okay. So when we talk about doing an LDR instruction, that's how we actually get a 32-bit value into a register. It's by establishing a literal pool. Now, let's go ahead and talk about how we might go ahead and print this out. So, first up, we've been using these mythical codes, and I've been telling you what the offset is. If only there was some great way for me to find out what the offset for a given Syscall was. God bless Linux and the fact that they give you the header files that they want, and they actually comment them. Here you see, in this particular case, unistandard.h has every single one of the system call instructions that are there, or every single one of the system call functions that are available to you. And then it actually tells you the location. So you have the system call base plus 4, plus 146, plus 273. That's the offset that you're going to want to put into R7 if you're calling the system call. Okay? So, for us, let's go ahead and use the right system call. We're going to print out hello world. Okay, so we find the right system call. Notice defined in our right system call base plus 4. Everybody sees this? Cool. The next thing we need to do is we need to figure out what does the right system call expect to get back? All we have to do is we can go over to our just command page, or if you want to, you can go over to some website and find out exactly what writing expects. In this particular case, it takes a file descriptor. So in this case, we're going to use standard out, which means print out in the console. It takes in the address of the buffer you want to print and the number of bytes that buffer is. So we're expecting 3 parameters to go in. So at this point, I know I need to populate R7, R0, R1, and R2. Okay? So it's the 5th entry into the Syscall table. Its offset value is 4. It takes 3 parameters. So let's go ahead and set that up. This is a straight example that you can see. Basically, what we have is we've got a .data section. I'm declaring my string as a label so that I can access some amount of data. The data that I give it is an ASCII 0-terminated string. It says hello world. Then I call it .align as the simpler, basically the simpler instruction to say, okay, now I'm done with that realign. This is where we're starting from the beginning for when we're starting to look at instructions. .text is just saying, these are my instructions. .global underscore start is saying, the underscore start part of this should be visible on everybody. That's all global is doing. Everybody should be able to see stuff. We're doing this because in a minute we're going to go ahead and link this file, and if you don't make it global, you're linked with it. Then I go ahead and say this is the start of whatever it is we're doing. The push instruction we kind of skipped over, and I wanted to go ahead and continue skipping over it. But basically what that does is it takes the value of all of the registers that I care about and it saves them off to the stack. So that I can do whatever I want to the registers and I don't worry about screwing the next person over. Now, we do the right. Standard out is the value of 1. Move that into R0. Move the address of my string into R1. So LDR R1 equals my string. That's going to set up a literal pool at the end, the offset that we need. We're going to move 14 into R2. 14 is the number of characters in the string I want to write. We're going to move 4 into R7 because that's the offset in the Syscall table to the right instruction. Then we want to exit the program. To exit the program, we've already talked about how to do that. Move 1 into R7, move 0 into R0, and then call a service code. And frankly, at that point, it's not going to matter what we do when we repopulate the stack or repopulate the registers. Okay. Now, I'm about to try and do a live demo, but in case live demos hate me, this is what we should see. Basically, I went ahead and catted out the code that we have, assembled it, loaded it, and ran it. There's absolutely nothing that will keep that from falling off. Nobody can see this, can they?
No.
Didn't think so.
Over 9,000.
Well, that's a very good. Is that it?
Yeah.
Okay, so go ahead and see what we've got listed here. So basically, I want to go ahead and assemble this to an object file. So just Derby. As long as I keep it straight, it's fine. Double check that. about how we should match at the same time as your content like about. And hello. Yeah. So, are there any questions about what we did? Yes.
Yeah, on the previous slide. Just explain, well, yeah, just explain what the AS and LP.
Sure. So AS is the assembler. So basically, in this particular case, we're assembling our assembly file to an object file. So that's where the .o comes in. If I remember correctly, I run away from my mind, tag G is going to provide a debug version for us so that we can dump this into GDB. Then the LD is the linker. This is really kind of a stupid step, and it shouldn't really be that important because you can see what I'm linking to this file, right? Absolutely nothing. But you have to go ahead and run the linker through so that you get the binary file that's executable. Does that answer your question? Yeah. Okay. Anything else?
What's the LDR call?
The LDR call, that's basically, the only thing the LDR call does is the LDR call will pull something, a 32-bit value out of memory, and will dump it into,
Okay.
and it'll pull a 32-bit value out of memory. There we go. And it does that by creating an offset to a location in memory that stores that 32-bit value, and then references that in the instruction, references the offset to that 32-bit value, so that you can then take that 32-bit value and dump it into the register.
The 64-bit version, do they have the same rules for fixed set, instruction sets?
No idea. Since there's only one chip out there that's 64-bit right now, I haven't been able to get into that. Not to mention the fact that I don't know if we can get into that, but I'm pretty sure if I spend another one, give me an iPhone to play with right now. Anything else? Okay. That's all I got. One last thing, because you guys are all walking out. Whoever comes up and gives me the best way for me to improve this talk gets one of our Raspberry Pi thumb stations that may be sitting at our desk. So come up, give me the best way for me to improve this talk, make it better.